Cool. Okay. So today I wanted to talk a little bit about the spark igniter and how it works. Is that okay?
For sure. Yeah.
Okay. Um, so right now, the spark igniter, I guess we'll draw a diagram. So we've got the LRE, it's doing its own thing, and then over SPI, we have our current spark igniter. And originally, when given this, we needed a way to sort of tell the spark igniter what states it's set. It has an ethanol line, a gaseous oxygen line, and a car sparking jumper. I don't know what it's called. And we need a way to communicate that to like when to do it. And we need to receive data in the form of pressure transducer readings and stuff. And sensor readings. The problem was originally we were using an Arduino Uno, and that only has 8 byte or eight, I guess, 8 bits SPI. So what that meant is for every SPI transaction, we can only sort of guarantee 8 bits that are sent or received. Anything more than that, we'll have to the Arduino Uno, you'd have to like build a queue and stuff, and there's no guarantee that it's really stupid. Basically, long story short, in the Arduino Uno specifically, we can only have 8 bits of data transaction guaranteed at once. So when I designed the like communications, how they're talking to each other, uh, I made the assumption that we can only send and receive 8 bits. Now we ended up using a feather. So yeah, we're on a feather. So technically, this should have the hardware to support like multi-byte SPI transactions. Which means you guys will have a little bit more freedom. You'll be able to send and receive more data. But when you see like the weird stuff going on, that's why the 8 bits is why it's going on. Okay. So I what's the best way to do this? It's sensor monitor. This is electronics. Matter set state. Yeah. So the message in the send direction will go one. So there's the send bits. Yeah, I guess we'll go like this. And this is from the point of view of the pi. So in the send, we know we have 3 things we need to control, which is the SOV1, SOV2, and Spark. And just as a reminder, the notation we use is the odd stuff is for ethanol, and the even stuff is for oxygen. Yeah, that should be the case. Check fire procedure. Yeah, SOV1, SOV2. So it starts with the GOX first. Okay, whatever. The main thing to note is that this is consistent with the rest of our system. So if odds are ethanol, which it should be, so the ethanol PT is odd and the ethanol valves are odd, then the igniter valve SFU1 is also odd. The same for SFU2, that's even, and then spark is its own thing. And I define these in these should be in sensor batch structs in the header file. So anyway, how it works is what I did was I selected the top 4 bits as the actual message, and then the bottom 4 is for error correction or error check. And so the bottom 4 bits, they're only affected by the top 4 bits, but it's not the other way around. And so we actually only really communicate with these 4 bits, and then these 4 bits are just to define whether or not we've if we've properly received the message. And I wanted to avoid something where it was like 0 0 0 0 0 0 0, which in this case it would be if like the this is if the line disconnected. We don't want the igniter to like be set in a bad state. Or I guess this one doesn't really matter as much because it's because it'll just shut off. But in the case of 1 1 1 1 1 1 1 1, this might be a case of like we accidentally shorted the line high, and we don't want to like set off our gas, aux, and spark igniter all at the same time. So we wanted to avoid this. So what I did was the SFU1, SFU2, spark. Yeah, if you see here. So the first bit is always 1. And then the next 3 bits are, I guess this is 1, X, X, X. And stop me if you're 1 exclamation. So this is simple. Since our SOVs are either on or off, we have a 1 or a 0. So this can be 1 or 0 for each of these states. The first bit is always 1. And then this is how we control it. We parse it. So if we want like our SOV2 on, which is our oxygen, but our SOV1 and spark off, how would we, like what message would we send? I can't hear you right now.
Oh, sorry. If you wanted like a certain configuration, did you say?
Yeah, let's say we wanted SOV2 on, but SOV1 and spark off. What would these first 4 bits look like?
1 0 1 0.
Yep, perfect. And then with the next 4 bits, since they're for error checking, what I made it do was this should be latch funcs. Bits equals the message. Yeah. So I took these 4 bits and then I inverted them. So I guess not. And then I put them in. So you remember in 352, you can like not a number of bits. So in this case, you have, let's go an example. So as before, you have 1 0 1 0, and then what would the bottom 4 bits be? Again, I can't hear you if you're talking.
Oh, I just lost connection for a few seconds there. We're back.
Okay, so let's say the same thing as before, SFU2 on, SFU1 and C or spark off. The bottom 4 bits, all it is a knot of the top 4. And that's our like very simple error checking method. So what would the bottom 4 bits look like?
It's flipping that first one as well, and that should it's not going to be it'll be 0 1 0 1, or it'll be 1 1 0 1.
It would be 0 1 0 1.
Oh, 0 1. Okay. It's just flipping that front one. Okay.
Yeah.
The leading one, the leading. Okay.
And if it was like this, it'd be 0 1 0 0. So you just take the first 4 bits and invert them.
Okay. Yeah.
So
now I can see what you're saying about the 1 1 1 1. And if we have that case,
yeah, it would be 0 0 0 0, and then yeah. So that's all that this is. It's just we use igniter set state, and we take the SOV1 as 0 1, SOV2 as 0 1, and spark as 0 1, and then it converts it into this byte format. And it writes it to IGN message. So what we're doing is every single yeah, that's all that's doing. And so I need to find. So if you check your sensor batch structs, I added a thing to sensor batch where it is the IGN MSG. This is how we talk to and from the igniter. So what we do is we load a value in here, and then we send it off, and then we should parse it back. But like when we want to
so something what we're doing is we're sending our 8 bits basically, but I guess on the receiving side it's I guess primarily looking for our ABC, I imagine. Is that
yeah.
Is that the case?
So we'll talk about the receiving side in a second. So here, this is what it looks like in sensor monitor. We read from the IGN message block, and we put it in like a buffer here, and then we actually do an SPI transaction to the device, and then we have the result that we get from it, and then we do some math. We don't actually write the IGN message the response. I've made a mistake. What we do is we directly do a little bit of math to get the pressure transducer values and the thermocouple. And then we put it in IGN res. IGN res is just a bit it's just a like we use this for a diagnosis. We don't really use this in practice. Anyway, on the receiving side, we'll look at the Arduino code. So what it does is it has a setup where it sets up all the pins and stuff, and then this is how you do the SPI communication in using a Feather, which is the microcontroller we're using. So it's either Arduino Zero or Feather, and we're specifically making it an SPI slave. So it's important that it has to be a slave so it listens at the right time. And then here we have the buff is the kind of like the message thing. Here, what we have, this is a double check to make sure that our sort of error code is correct. So if this is not correct, so let's say you got all zeros, then it would just completely ignore the message update. It would ignore whatever the command is. So that's why, yeah.
It's just the condition that you said.
Yeah, so it's the not thing here. So it takes this and makes sure that the bottom is the not of the top. And then if that's good, then you can keep going. what we also have is a timeout similar to the Arduino watchdog. It's basically if there's been too long since the last message, then we basically time out. We say like, oh, something's gone wrong, and we just like close everything. Yeah, if you receive a wrong input, then I think it shuts everything off. Yeah. So if you also time out, then it just like closes all the valves on the igniter. And just a reminder, sensor monitor is constantly running. So whatever you put in IGN message, that's going to be constantly sent 130 times a second, the same message, until you change it. So that's how we guarantee like, okay, we're like, in case we have a single miss input, it's not a big deal. We just fix it right after. But that's like, we make sure we have a constant kind of open communication. Anyway, and this is a switch case. Our read val is the sort of like actual command. So this one ABC. And then for each case, I couldn't find a better way to do this, and I was short for time. So again, the one is always on. If the one is off, then you set everything off. But yeah, like in this case, it's 0, 0, 1 is SFU1 off, SFU2 off, spark on. 0, 1, 0 is off, on, off, and just like that. And then on the way back, it has some, or for this, the serial com handler, this is specific to the how to use the feather as an SPI slave. This is the same as it's pretty much the same on every SPI slave code. It's like I didn't change any of this. I just got it from G and Travis and Harsh.
Like an initializer kind of, or is it?
This is the handler function. So the initializer is at the top here.
Yeah.
But this is actually like tells it what to do with all the like buffers and registers and stuff. I didn't bother like changing this. I just used what they gave me. Again, the last thing, okay, we'll talk about the receive now. So the receive, we have 8 bits, and we don't really care if the message is incorrect since we're just like watching it. So we'll use all 8 bits. And how we did this is heating them. So 2, 3, 4, 5, 6. Down 1. Yep. Okay, so those are all the PT, num, and then PC. So what I did was this is just some like binary math. We basically needed to convert a value from 0 to, I think, 1,000 PSI. Scale factor. Yeah, I don't remember the specifics. Basically, we need to store a range of 0 to 1,000 in 6 bytes. And let's see. Maybe it's here in sensor monitor. Sorry, 0 to 150 PSI. So 0 to 150 PSI in 6 bits. So this was the same dilemma. We can only send and receive 8 bits, but we needed to know the PT values for the ethanol and GOX. For I think it was gaseous ethanol, maybe. I don't remember. So that we can know like how much pressure to use. And since I was communicating with Amraz and Kabir, on like manually pressurization. I needed to know this value. So we settled on, well, since we're not going over about 100 psi, our range is going to be 0 to 150, and we didn't map that to 6 bits. So what we decided is, if we have 8 bits, we need 1 for the thermocouple to use. Like, our plan was to use this like, oh, this is going to be 1 if we have a flame and 0 if not. We didn't end up using this for control, but we still have it implemented. And then n is the PT number. So what we do is we alternate this between 0 and 1, where if we have, I don't know, 1 0 0 1 1 1, and then if this is 0, then we assume it's PT. Yeah, we do the same odd and even. So if it's 0, we assume it's PT2. There he is, PT0. Oh god, that was stupid. We use the same odd and even. So PT0 should be GOX, and then PT1 should be ethanol.
Yeah.
Yeah.
PT1. Yes.
Yeah. So in this case,
we consider 0 as even.
Yeah. And so this would be the PT value for GOX, and then the subsequent message right after might be something like this or something, and that's the PT value for ethanol. And so we'd alternate this in the message back and forth as our kind of like bits, so we can send effectively like twice as much information. Anyway, so the first 6 bits is our PT value, and this is in binary. We have, this is like a number from 0 to 64, and we just map that from 0 to 150 psi. And then n, as before, is the PT number, and then T is the thermocouple. Whether it's on or off, that's all we care about. And here in the code, we have, if it's non-zero, so if it's 1, then we assume it's PT1. Then we extract that bit by using like an and we calculated this adjustment scaling factor in field. You'll find that typically this is the case where you'll have your theoretical scale factor, and then, which is 150 over 64, and then like there'll be some adjustment you'll have to do. So in this case, we like went in field and we measured and found that like multiplying by this just gave more accurate values. And then we split it up, so IGNTC in sensor batch, that's just if it's on and stuff. And yeah, now back to the Arduino code. So if we look, it's, we analog read the kind of PT value, which in our case, he was using a voltage based PT value, PT. So we didn't need to pass it through a resistor or anything. We just directly read the voltage on it. And it scaled from 0, like it had a linear scaling. So like this is, I don't know, input would be voltage PSI. It would basically be a linear relationship. And so that kind of made it easy. And so this, we're just kind of, I'm dividing by 16, so it goes from 8 to 6 bits or whatever. Or no, since it's Arduino, in by default, it reads analog values in 1023 as the max. So 1023 divided by 16 is 64. So I'm talking about this 1023 Arduino analog read val max. So that's that. Divided by 16 equals 64. And so that's how we can map to 6 bits instead of 10. Yeah, simple. And then we take that value and we send it over. And we also, it's not currently using the thermocouple right now. And the reason is because the thermocouple code, if no TC because I2C has no timeout. So I2C has this quirk where it's not designed around there being errors in the communication. And since this was something shitty that I kind of like soldered and breadboarded together, I didn't know if I didn't feel confident that there might not be like a wire that comes loose or something, or like the chip itself burns out. Because how it works is when you try to do an I2C message, you send it, and if you want to receive a message, you sit there and you wait infinitely, and you can't do anything else while it's doing that, or at least not in a like simple linear program. It'll block sitting there waiting until it receives the proper like ACK acknowledgement ping. So there was a case, or there was a situation where I'd booted up, and if the thermocouple wasn't working like right away, then it would freeze the entire program. And I didn't want to take that risk, so I just kind of removed it. This is something that you'll have to like look at as a like risk and like code around it. There's ways to code around it. There's like you can code your own timeout. You can do things in parallel. You can use a different kind of thermocouple or a different like, or doing it like this is a just something to solve. Do you kind of get what I mean?
So what is the concept for like timeout?
Yeah. So
Is that just like delay, or is it like um
it's basically like if you send a message, how long do
yeah.
you wait before saying like, okay, the receiver didn't receive it or something? I'm either going to resend or I'm just going to move on.
Okay.
Yeah.
Kind of like what our watchdog has.
Basically, yeah. It's a communications. It's pretty much a packet watchdog. Yeah. That's the right idea.
Okay.
There we go. Yeah. So here there's like A sends a message and B has the acknowledgement for this first one, then A sends another message, but it was lost or something, or B like died or something.
Yeah.
And then you need to like, how long do you wait before either sending another message or moving on? So that's the time.
Yeah. I think the argument was doing something like function or whatever it was. I remember it was able to keep track of the time. I think we had an interval that we set like a delta or whatever it was, half second or something.
Yeah.
But okay, so I2C I guess doesn't have this right.
The hard part with that is like, well, we'd have to like code it directly into the I2C library or something, because if you call the function's going to wait because internally it has a loop waiting for the response, and there's no timeout in that loop, so it'll just keep waiting until it gets a response. So we'd either have to modify it or do like, we can load it in RTOS and then have it so like things are running in parallel, or that's up to you guys to decide. You can also just say we don't want a thermocouple on the igniter, which is probably the simplest. This is what I did for this. Yeah.
But okay, but definitely something to look into. I just never read this. I2C timeout.
Yeah. And again, it's only one pin for the thermocouple because I think I had it set as the minimum temperature was like 80 degrees Celsius or something. Like anything above that, we send a 1. Anything below that, we send a 0.
Oh, okay, fair enough. Yeah.
But yeah,
just like flame, or we have the igniter, you know. We have something.
Yeah. So the I guess the risk was we didn't want to use all our pressure, and like I guess we didn't want to fire our entire like engine if we didn't have a confirmation of igniter. But the igniter ended up being really consistent. Like we didn't have any like misfires where the igniter failed to ignite. So we just kind of like YOLO'd it and it worked the day of. Some small considerations is emergency stop is built into this. So if we look at it should be in, yeah, latch funcs is also where I put the igniter stuff. It should be, Igniter set state. I guess it doesn't look it in here. I guess it's in sensor monitor. I did a simpler one. So if I look. Yeah, igniter set state 0. So it doesn't lock anything out, but like when you set emergency protocol, it also like constantly resets the igniter state to 0. Yeah, and that's the SOV 1 and 2 are closed and the spark igniter is off. A few more things. Right now, it's currently on the old IMU line. So should be here. Yeah, 23. You'll have to look it up. It should be IMU 1. Oh god. Yeah, old IMUCS. Okay, so this is in IMU2 slot. Or no, this is in the IMU1 slot, and then I moved the old IMU2 to say that like we don't have the other stuff. So in the IMU1 slot, we put the igniter because we're not using an IMU. Other than that, we don't want to leave the sparker on for too long because it might burn out. But that's really pretty much everything. That's just our fire procedure. In latch funcs, we also had a like burp function. So yeah. So we called it short ignite, where we'd start the ethanol, wait 0.2 seconds, start the GOX, wait 0.2 seconds, start the sparker, wait 0.2 seconds, and then turn it off. And that's just the test. If it's working, we can like burp it. But yeah, that's pretty much it. Do you have any questions?
I just thought last one that short ignite is that just going through the it's like the one is that igniter set state. Which one is that actually?
So this is the function. This is latch funcs, by the way.
Yeah.
So this is the function. What it is SOV1 state, SOV2 state, and then spark state.
Okay.
So we have SOV1, SOV2, spark. And so that's ethanol, GOX, spark. And it's kind of dumb. I was stupid in that I named it IGN PT0 and 1, but then SOV 1 and 2. Just remember that even is oxygen and odd is ethanol.
Okay, so PTs are 0 and 1. SOV
yeah, PTs
we have
are 1 and 2. And then SPRK is the like I think it's like a card spark plug or something. Do you have any other questions?
Yes. So moving forward, is the idea talking to Bradley, it's like in terms of the igniter, I mean a lot of our changes will probably come in the hardware. It's probably just like something we change externally or whatever it is. But it sounds like are we changing much on the software or
so that's up to you guys to see because there are upgrades you can make, namely with like receiving like either putting more sensors on it or receiving like higher resolution PT values and stuff. And like the thermocouple value, it doesn't the temperature is just 0 or 1. We can probably do more. But the main focus right now is like talking to them about their specific hardware setup and integrating theirs. Like you can use this code. I'd recommend using like some kind of skeleton like this. But whatever you guys think will work best and simplest. because like this setup is made like there's like I don't know if you've seen the spark igniter controls. But it's like a flat plastic box.
It's a tub, right? It's a plastic tub.
Yeah, the tub, and there's
Yeah,
like
yeah.
wires in and out of it and stuff, and so
Dude,
like
that thing was awesome, man. That thing was so awesome, dude. Had some like holes in it too and everything.
yeah.
It looked good, man. It looked awesome. Yeah,
No,
yeah.
I Kabir
Yeah,
gave that
yeah,
to me, and then I yeah. So
um,
you'll be talking to Xander, and I know G messaged to like talk about to Xander's team about the sort of like hardware. That'll affect kind of like what it's doing. And just to remember, like this kind of receiving setup was simply because we only had 8 bits to work with. But if we have more bits, like if you guys should be able to do multi-bit transaction or multiple bytes, sorry. So like 16-bit or 32-bit or something. And then you just like write the handling code in sensor monitor and like update the like latch functions and stuff.
write more bits with that.
Yeah.
Write more bits. Is that something that we can code, or is that just the feature of the microcontroller?
So the Arduino, the way the hardware it was built with doesn't support multiple byte transactions. You can do it, but it's kind of hacky and it's not 100% consistent. That's why I wanted to avoid it. But especially as an SPI slave. But for the Feather, it should have hardware buffers where it can store multiple bytes in a single transaction. And so like you'll have to update the code to like allow it to do that, I think. But like I don't think it'll be huge complex. That's something I think G and Travis could probably handle.
Sure, yeah. I'll definitely kind of
yeah,
lay that
but
information to them. Yeah.
We'll say the main focus would be to like transfer this code to something that works with Xander's hardware and planned hardware. And then update the sort of sensor monitor kind of whatever like Pi backend. And then we can go on to like updating the functionality. Or you could just like move directly onto like the other kind of LRE projects first. Whatever you guys, wherever you want to allocate your time. The most important thing for this is that it works and you can have a pressure reading from the GOX and ethanol and control the valves on the igniter. Everything beyond that is kind of like icing. I'll be saving this and uploading it to YouTube and then putting it in the software LRE channel so the other guys can have an idea of like what.
I think for me, a lot of that scaling factor is probably something that I'll be a bit unfamiliar with. It sounds like you kind of derive these values from, or kind of got these values from kind of testing and stuff like that.
Yeah, that's. I think that might be some of the like less important. Like it's just like math. If you sit down and like write it out, then it won't be that bad.
Okay, sounds good.
It's like,
question. Oh, sorry.
If you want to know, in this case, analog read.
Yeah.
Returns a value from 0 to 1023 based on a voltage from 0 to 3.3 volts. In this case, 3.3 because it's a Feather. And so the pressure transducer we were using also mapped a pressure of 0 to I think 1000 or like 150 or something as a voltage from 0 to 3.3 volts. So all I did was take that, instead of 0 to 1023, I wanted it to be 0 to 64. Yeah. So I just divided whatever value we got by 16 because 1024 divided by 16 is
okay.
Yeah. Like if it was directly in the middle as 512, it would be, we'd get 32 as our like scaled output. So that's all that's doing.
Okay. 0 to 1000 kind of you can say kind of potential like points between 3 points.
Yeah, the resolution. And that's just default in the Arduino, how the analog read works.
Okay. Yes.
Okay.
It's probably just a dumb question, but most of the stuff is it in so latch funcs and then
So
sensor
it's
monitor and with the structs as well in the batch.
yeah.
Sensor
So
batch structs.
latch funcs is the sort of kind of like control the like sending messages to it. Sensor monitor is kind of how we parse the messages, and we gotta, this is too big. We probably should clean it up. But it's here, 172 to 193.
Okay.
And then sensor batch structs. This is like small things like the defined PT chip select and stuff. And then this is fire procedure. This is just an example of how it's used. We don't really care about that much. This is something that Kabir and I like in the field. I don't know if you remember, like,
yes.
yeah, that was like 40 minutes of us delaying just to
You
get
guys are
this.
talking a lot about timing, right? You guys are talking a lot about the timing, right?
This is
Like
down
how
to like millisecond by
Yeah.
millisecond.
That's right. Yeah.
And then the last thing is the code on the Arduino itself. I put this in the Spark Igniter repository, so you should have access to this.
Yeah.
It's under Marko integration branch.
Okay.
And it's the feather SPI.io.
Just
okay.
Just kind of knocking down the places to look at least. Yeah, appreciate it.
Yeah. Gavin, you're a maintainer, so you should be okay. I'll stop the recording for now.